All right, welcome back to the morning session, third talk of the morning session. I have the pleasure, well, not only the pleasure, but the pride to introduce the next speaker, Carl Lian from Berlin. He's dialing in from Berlin.
Actually, I'm in Zurich, but
oh, you're in Zurich. Okay, sorry. I guess from the name you can kind of guess how the next speaker and I are related. Indeed, we are related. I think he's the only person who is probably the youngest and someone I know the longest among all of us today here. I guess I've known Carl for let's see, 29 years. Okay, so he's going to tell us about counting curve in a fixed domain.
okay, so thanks a lot. Thanks to my dad for the introduction, and to the organizers for accommodating my kind of hectic travel schedule these days. So I should maybe warn the audience that I'm only dialed in on one device. So I think for the Zoom audience, I won't be able to see your questions, but please feel free to interrupt me. And of course, I assume if there's a question from the in-person crowd, someone will interrupt me. But okay, so I want to discuss some kind of class of problems in enumerative geometry that to me, I think live in a very interesting place because they draw both in a very real way from kind of virtual invariants, which are kind of innovations of the last 30 years or so, as well as some very classical geometry. A lot of these results are very much in progress, and I will mention some names along the way. Okay, so let me set up the main players. So to begin with, I will always work with a smooth projective variety, which I will call X. And I will use the letter R to denote its dimension. Okay, and then I'm going to fix a set of general points on X, X1 through Xn, and a curve class on X, so some kind of interval second homology class. All right, so this is sort of the usual Gromov-Witten theory stuff. And then I'm going to fix a general curve with n points on it. Okay, so this general curve will have genus G. This number n is the same, we can see what I'm writing. This is the same n as the number of points on X. And I want to emphasize that this curve is fixed, okay? And I'll also assume it's general in moduli. Okay, great. So the question I want to ask is how many curves on X can I find that have complex structure equal to the curve that I've fixed, okay? So in other words, how many maps can I find from my fixed curve to X that on the one hand send my mark points on the curve to my mark points on the target variety, and on the other hand, live in my prescribed homology class. Okay, so in the usual Gromov-Witten theory setting, I don't fix the complex structure of the curve. I just ask for curves of any complex structure. But here I've required my curve to have some fixed moduli. Okay, so let me restate the question as follows. So I'll take the moduli space of maps, which I denote MGN X beta. And this has a pair of forgetful maps. So on the one hand, I can remember the complex structure of the domain curve. And then on the other hand, I have n evaluation maps that remember the positions of the images of the mark points on the curve. Okay. And so I define this map tau, which remembers both pieces of information. And in order to get a reasonable question, a reasonable numerative question, I should assume that this map is, I call virtually finite. Okay, so morally, I want the dimension of the source and target to be equal. But as is well known, the dimension of this source, the dimension of this moduli space of maps can be somewhat wild. So the best I can do a priori is just write down an estimate for its dimension. So if you write down the standard expected dimension of the moduli space of maps and set it equal to the dimension of the target, which is something that's known, you get some numerical condition. Okay, so under this numerical condition that the degree of beta against the anti-canonical of X is equal to something, you at least hope that you have some finite morphism and you can count the number of points in each fiber. So when this happens, so when it happens that tau is both expected to be finite and is actually finite, which is to say that over a general point of the target, I really do see kind of a finite reduced set of points, then I ask for its degree. Okay, so a point of the target is like a pointed curve and a bunch of points on X. and then a point of its fiber is exactly a map as I've asked for. Okay. Okay, so when this happens, so when all dominating components of the source have the correct dimension, then I denote the degree of this morphism or this curve count by the so-called geometric Tevlev degree of x. Okay, and I denote this Tev x g n beta. Okay, so importantly, I don't require that my moduli space of maps actually has the right dimension, but I only care that it has the right dimension over a general point. Okay, so I allow it to have components that are very wild, but that sort of only live over special loci of the target. I just throw those out. Okay. All right, so this is the first curve count I want to think about. And so you might be wondering about the name. The name, we've been calling these Tevlev degrees as a result of Genya Tevelev in 2020, where he was doing various things with scattering amplitudes and so on. But one of his auxiliary results was a count for P1. So he found that if you count, so these are maps to P1, so basically branch covers of P1 out of a fixed curve of genus G. And if you kind of set the, if you consider maps of a very special degree, of degree G plus 3, degree G plus 1, which requires you to have G plus 3 marked points, then he found that you always have 2 to the G maps independently of, well, for all G. Okay. And so actually it's fitting that I'm here in Zurich because Tevelev gave a talk at Zurich. So this sort of got me and my collaborators interested in kind of thinking about this problem for various other target varieties X. Okay. Okay, so I've already set this problem up in terms of the moduli space of maps, which lends itself to kind of obvious second direction, which is I can compactify this space. So now let me introduce the analog of these counts in Gromov-Witten theory. So I'm going to do the same thing as before. I'm going to take this map tau, taking a moduli space of maps and remembering the evaluations of the mark points and the complex structure of the curve. But I've now put a bar over everything. So now I've passed to the moduli space of stable maps as opposed to the moduli space of maps out of a smooth curve. And again, I'm going to assume that this map is virtually finite. So I'm going to assume that at least I expect finite fibers, which I can count. And so you might think, well, okay, I've just compactified everything, so I shouldn't the degree to change. But in fact, what changes now is I gain access to a virtual fundamental class. So what I can do now is that I can say, well, I have a virtual fundamental class living in the expected dimension of the moduli space of maps, even if that moduli space of maps has wildly the wrong dimension. So whether that be on dominating or non-dominating components. So even when this map is virtually finite, but fails to be finite, I can still make sense of virtual fundamental class rather than a fundamental class on the source. And then I can push that forward and expect to get, or I know I'm going to get a multiple of the usual fundamental class downstairs. And so that multiple of the fundamental class can be regarded as what you might think of as the virtual degree of this map. And so that rational number is, by definition, the virtual Tevelev degree of X. Okay. And the thing I want to emphasize here is, again, even if somehow you have out of no transversality in sight, because of the existence of this virtual fundamental class and because it has good properties, I can make sense of this degree, even if kind of I don't actually see a multiple, kind of a finite union of points. Okay, so I've defined kind of two versions of the same counting problem. One is sort of a geometric version, where I'm, evaluating I'm asking for the cardinality of an honest finite set. And the other version I'm passing to some kind of virtual count. Okay. And okay, so now, all right, this lends itself to three questions. Okay, so I've defined for you two counts. So question A is I can ask what's the virtual degree. Question B is I can ask what's the geometric degree. Okay, so when I have this this additional transversality assumption, how many points are you actually seeing? And then I can ask a third question of, are these two notions of curve counts equal? So let me just say a little bit. So as I've written, the virtual question somewhat unsurprisingly reduces to a computation in the quantum cohomology of X. So the idea here is that unlike in kind of traditional Gromov-Witten theory where I have a varying curve, I'm asking about virtual counts out of a fixed curve. So I can take that fixed curve and degenerate it to some kind of essentially genus 0 object. And this kind of translates well into the language of quantum cohomology, and you can write down some very explicit formula in terms of quantum cohomology. Now, whether you can actually evaluate that formula in practice for some examples is a different question. And so the first, at least in this language, the first work in that direction was due to Anders Buch and Rahul Pandharipande last year. But in fact, this is somehow a much older question that people have been thinking about in various guises for the decades before. Okay, but the point is that if you have a kind of sufficient understanding of the quantum cohomology of X, you can really compute these invariants. At least you can kind of turn on your computer and get numbers. And then from there, you can try to hope to prove some general formulas. Okay. On the other hand, these kind of classical counts, which are counts that perhaps the 19th centuries would have thought about and actually did think about in various guises, these are actually a little bit more subtle. And somehow, despite the fact that there's a lot more machinery that goes into defining the Gromov-Witten invariants, somehow once you have that machinery, then the computation is completely algorithmic on the Gromov-Witten side. But if you're asking for these honest geometric counts, in fact, those tend to be more difficult in many, but not all examples. Okay. And then, then there's the question of, well, when are these two notions of curve counting are actually equal? And that's actually the question I want to focus on today. And so I will make this a little bit more concrete and give some examples. Okay. So I don't want to focus on parts A and B today. So there's been various work on kind of both sides, and lots of formulas have been proven. And I won't really go in that direction, but I'll give at least one example, which is for when X is P1. So as you might remember from earlier, this kind of subject became kind of received some renewed interest after Tavelev's result for covers of P1. So the first results came for trying to study covers of arbitrary degree of P1. Okay, so the first thing I claimed is that if you understand the quantum cohomology of X, in this case P1, then you can compute these virtual curve counts very easily. And indeed, the quantum cohomology of P1 is something very easy. And we've known for a long time, in some sense, that these virtual curve counts are always equal to 2 to the G, independently of the degree. So Tevelev showed that there are, so he didn't call these Tevelev degrees, but he was essentially working on the geometric side. And he showed that there are actually 2 to the G maps out of a genus G curve with degree G+1 passing through the correct number of points. And so Anders and Rahul kind of in their paper worked out that in fact this is true virtually for all degrees. Okay, but in fact this was kind of known in the 90s to Bertram, Daskalopoulos, and Wentworth. In fact, even before the virtual class was understood as we understand it today. And this number also comes up in Yanda's work on equivariant Gromov-Witten theory of P1. Okay. So this is a fairly straightforward calculation. I mean, somehow the results in these papers are much more non-trivial, but this is somehow the first result you prove. Okay. But on the other hand, if you go to the geometric side, instead of kind of asking for a virtual count of curves, if you ask for an actual count of curves, the answer is a lot more complicated. So as you see, there's 2 to the G, but then there's a bunch of extra terms. There's a bunch of binomial coefficients. And it's not so important what they are, but what I want to emphasize is that, well, there's so the first term is like a G choose I from I equals 0 up to G minus D minus 1. So G minus D minus 1 can be negative. And so when this is true, all these binomial coefficients are understood to vanish. And in fact, from this formula, you see that when D is sufficiently large compared to the genus, then all these correction terms go away. Right, so what this is saying is that this virtual count is enumerative, right? It's equal to the actual count of curves when the branch covers in question have large degree, so they have degree at least G+1. But when the degree is small, I get sort of a bunch of junk. So I get 2 to the G minus a bunch of stuff. So maybe this isn't so clear, but in fact, these binomial coefficients, these terms are all negative. Okay. And so in some sense, this is an answer to all 3 questions above. So I've told you the virtual degree, I've told you the geometric degree, and they're equal whenever the degrees of the maps in question are sufficiently large. Okay, so these were computed by various people. So the first people to do it were these geometric degrees were Alessio Cela, Rahul, and Johannes Schmidt. So I should say, so all three of those people are based here in Zurich. So Alessio is Rahul's PhD student, and Johannes is Rahul's former PhD student. And then I wrote a paper with Gavril Farkas where we gave a slightly different approach that yielded actually different formulas from this, but of course they're equal. And then Alessio and I kind of considered a slightly more general version of this problem and also arrived at this formula. Okay, and so again, the thing I want to emphasize is that these virtual and geometric degrees are not equal, but they are equal if D is sufficiently large. Okay, and in fact, in my paper with Gabi, so we found that the same holds for higher dimensional projective spaces, and this was somehow, at least in principle, understood in the 90s to Bertrand Daskalopoulos and Wentworth, although they didn't say it maybe in these words. But again, it's true that if you count curves in a projective space of any dimension, and the curves have fixed complex structure, then the Gromov-Witten counts give you the correct answer when the degrees of the curves are sufficiently large, but not in general. Okay. And in fact, the kind of high degree counts are almost trivial, and the virtual count is almost trivial, but the low degree geometric counts are quite non-trivial. And this, so this I've written up and posted on my website, but this is not yet on archive. Okay, and so as I said, I'm not going to go into other kind of the other formulas that have been arrived at, but I'll just mention some other examples that I and various people have been thinking about that are interesting. So one can take various other target parties. One can take the X to be a homogeneous space, and this is actually a very long story, going through, actually coming from mirror symmetry and going through, kind of tracing through the development of virtual fundamental classes. These are more or less all on the virtual side, and I think it's a very interesting question to try to prove some results on the geometric side, which would be harder. So there are various results for hypersurfaces of low degree, so for Fano hypersurfaces. So Alessio and Anders and Rahul have some results on the virtual side, and I have kind of much more limited results on the geometric side. And then a more recent case that Alessio and I have been thinking about have been various blowups of PR and Del Pezzo surfaces and so on. Okay, so as I promised, the real question I want to focus on is not these curve counts themselves, but the question of whether they're equal. So the next thing I want to do is, well, give you some indication as to why they might not be equal. Okay, so why would this Gromov-Witten count fail to actually give you the kind of desired geometric count? And so I want to explain this example for a projective space. And so the reason it's not so surprising, the point is that when one considers these virtual, invariants, there are lots of boundary contributions, right? And these boundary contributions are often positive dimensional, right? So when you're asking for a degree, you don't get a kind of a number of points, but rather you get some kind of excess class, which you integrate. But unlike in Gromov-Witten theory, these kind of boundary contributions, when you restrict to curves of fixed complex structure, tend to appear less often, right? And in particular, they tend only to appear when the degree is quite small. So let me give a concrete example. So this is here I want to think about maps to PR, and so the numerology here is that n is so n is, well, it's this thing. And so it's one slightly confusing thing. And so the claim I want to make here is that when D is small, so when D is at most 3G, RG, excuse me, then I can make some kind of maps at the boundary of the moduli space of stable maps that are at least morally out of a curve of fixed complex structure and a map to general points on PR. And the confusing thing is that under this numerology, so I have D on the left side of this left-hand side of this inequality, and I have D on the right-hand side of this inequality. So one way to think of this is that the degree is very small compared to R and G, but on the other hand, D is large compared to the number of mark points. And actually, that's what I'm going to use. And the reason for this sort of disparity is that, well, here you see that N is growing faster than D. So when D is small, then N. When D is small, it's actually larger than N, and then when D increases, it becomes less than N. Okay, but in any case, the point is that, well, these maps at the boundary of the moduli of stable maps, well, notice that, so I require that my map is coming out of a fixed curve of smooth domain. But in fact, in the moduli of stable maps, you remember that, well, actually, these stable maps don't actually come out of curves of smooth domain, but rather out of curves of smooth domain after some kind of contraction of non-stable components. So at the boundary, I do have maps with non-smooth domain, which kind of look like they're coming out of a curve of smooth domain from the point of view of this problem, because all of these rational tails are contracted under the stabilization. So when n is at most d+1, I can play the game where I can take a ghost component, right? So I can take a component of degree 0, and this is a curve of, this is sort of any curve of genus G, and I can map that curve of genus G to just one of my mark points xi, pr. I can just pick one of them. And because my number of mark points is small compared to the degree, I can then connect that marked point to the other mark points, right? So these rational tails are now, you can imagine these rational tails mapping, for example, to lines on PR. And so the result now is now I have a rational, now I have, so now I have a stable map of degree, let's see. So it's a stable map of degree n, or at least n. And because n is small, I can arrange for that degree to be equal to d on the nose. And that gives me a stable map of degree d, right? That does not live in the moduli of stable maps with smooth domain, rather the moduli of stable maps with singular domain. And that will contribute to my virtual Tevlov degree, but it will not contribute to my geometric Tevlov degree. And in fact, because these maps out of these rational tails will typically have degree greater than 1. In fact, I'm going to get positive dimensional moduli here. So in fact, I'm going to get infinitely many contributions to this virtual degree, and they're going to be kind of integrated out to get some number, but that number will have nothing to do with the actual geometric count of smooth curves. Okay. So the point is that whenever you have components of the boundary, so of the moduli of stable maps dominating mgn bar across xdn, then what you should expect is that your virtual count is not going to be enumerative. It's not going to agree with the geometric count. Okay. And so one of the interesting things here is that, of course, this happens a lot in Gromov-Witten theory. But in fact, when D is large, this does not happen, as one can check. And this was kind of worked out in my paper with Gabi. But not only that, even in the range where these virtual counts are not enumerative, the geometric count still makes sense, right? So notice I've given you infinitely many maps, infinitely many stable maps at the boundary, which kind of produce a disparity between the virtual and geometric counts. But in fact, there's still finitely many geometric counts. Maps. And in Gromov-Witten theory, it often happens that, in fact, the kind of what you might think of as a geometric count, in fact, there will be a lot of excess there too. And this doesn't happen typically, as I'll explain later in this talk. Okay, so the game here with PR is that when D is small, my virtual degree includes boundary contributions and is therefore not enumerative. But when D is large, this doesn't happen, right? So you can kind of imagine when D is bigger than RG, which kind of translates to N being bigger than D+1, you cannot make examples of this type. Okay. So this was originally observed in my, I guess, first in my paper with Gabi, and then the expectation soon after this was that, well, you might hope for some arbitrary target variety if there's kind of enough positivity, right? So if your degree is sufficiently large, then you should expect kind of no boundary contributions to these virtual degrees. Okay, and therefore that they're equal to the geometric ones. Okay. So let me now package this into a definition. So X will just, again, be any smooth projector variety. And I will say that it satisfies a strong asymptotic enumerativity if, well, on the one hand, so question part A is sort of saying that the moduli of stable maps, so remember, I'm always assuming that I expect the moduli of maps to have the same dimension of the target of mgn cross X to the n. But the first condition is that, well, it actually does generically have the correct dimension, the correct relative dimension. So the first condition says that basically that the geometric degrees actually make sense. And then the second condition says that, well, when I now go to the boundary, so when I compactify everything and look for boundary contributions, I don't see any, right? So this is basically saying, so kind of Tev X, the geometric counts make sense. And then the second condition is roughly saying that, oops, is roughly saying that Tev is VTev, right? Because my boundary doesn't dominate, and therefore there are no contributions over a general point. Okay. And okay, so I need to explain this word asymptotic. So when A and B both hold, I both have a geometric Tev-Lev degree and it's equal to the virtual one. But I don't, as we've already seen, we don't expect this to hold always. But we say that X satisfies asymptotic enumerativity if this holds. So let me focus on condition 2 first. So we say that it satisfies asymptotic enumerativity if I have this enumerativity for all large beta, so in some kind of asymptotic range, so when the degree of beta is very large. And the strong part is that, in fact, I also require that when I'm in genus 0, that actually these are true in the nodes. So in fact, I don't even have to require D to be sufficiently large. So you see in this example above for PR, when G is 0, the condition that D is less than RG is sort of no condition. Okay. So I hope this definition makes sense. And the point is that, well, if X satisfies these properties, or it satisfies properties A and B, then my virtual degrees are enumerative, which is to say the geometric and virtual degrees are actually equal. Okay. And so let me just pause and say that. So when you can prove this for some X, in fact, the information can go in both directions. So I maybe won't go into this now, but there are examples where the virtual Tev-Lev degrees tell you something about the geometric Tev-Lev degrees that I otherwise don't know how to compute. And in fact, I have examples where I know how to compute a geometric degree, but I don't know how to compute the virtual degree directly without sort of checking these hypotheses. Okay, and so the conjecture, all right, so this is just a property of X, so I've made no statements, but the conjecture is that this property, this strong asymptotic enumerativity, holds for any Fano variety. Okay, so very roughly, I mean, if you should think of a Fano variety as being pretty positive. So the tangent bundle is, in particular, if you take any curve, it's positive against the tangent bundle. And when you have the additional positivity that the degrees of your maps are sufficiently large, then the expectation is that the geometric and virtual degrees agree. Okay. And so this was basically guessed by Rahul after kind of talking about my paper with Gabi. And we worked out some examples in which we could actually prove this. We could actually prove this conjecture for some classes of X. Okay, and maybe I'll explain a little bit later kind of where you might hope to use the Fano-ness of X, because this really is, at least as far as I can tell, somewhat important. Okay, so let me just, so hopefully the conjecture is clear. So let me give a list of varieties for which we know the conjecture. And of course, the conjecture is about Fano varieties, but you can still ask whether the conjecture is, or whether this property is satisfied by non-Fano varieties. And it's kind of interesting to see the extent to which you need the Fano hypothesis. Okay, so in my original work with Rahul, so we checked this conjecture. The main examples were for X, some kind of homogeneous space, so a G mod P, or for a hypersurface of very low degree. Okay, so let me emphasize the very part. So a hypersurface is Fano. So an R-dimensional hypersurface is Fano if its degree is less than about R, or maybe R plus 1. So the conjecture is that for all of those hypersurfaces, you have this enumerativity statement. But in fact, we can only prove it in a much smaller range, where when R is basically, so when E is basically the square root of R. So that's a very small kind of portion of the Fano range. Right? So there's a lot of room for improvement here. And I'll kind of explain where the roadblock is, hopefully, at the end. Okay, and then more recently, Alessio Cela and I have been thinking about blowups of projective space, and this led to some interesting examples. So we've checked the conjecture for Del Pezzo, so these are Fano surfaces, and this is not so hard. The conjecture is true for the blowup of projective space at any projective space at one point, right? So this is still a Fano variety. And then interestingly, if you take the blowup of P3 at 4 points, so if, for example, if you take the 4 torus fixed points, this is actually somewhat more non-trivial that these these counts agree. And the interesting part of this example is that it's in fact not Fano, but the conjecture is still true here. Okay, and I put a star here because there's some details that still need to be worked out, but I'm fairly sure everything is okay. And then one other interesting example as well, Del Pezzo surfaces are Fano surfaces that are blow-ups of anywhere between 1 and 8 general points on P2. One can pass to blow-ups of P2 at any number of points, which are no longer Fano. And the expectation here is that the conjecture is still true there, even though X is not Fano. And I can sort of morally prove it if you assume big conjectures that are kind of hopeless. For instance, certain bounded negativity statements. I say morally because somehow there's some steps I don't know how to do, but I mean, I'm fairly sure this is true. If you take a general collection of points in P2 and blow up, you get some kind of very non-Fano variety, but these curve counts should still be enumerative. Okay, so these are some examples where we know the conjecture, or we know this property. Okay, so there's been some doubt cast. So some experts have communicated to me that they're actually not so optimistic that this conjecture is true for kind of high degree hypersurfaces. But as far as I know, there's no proof yet. I'll kind of remain agnostic on it. But their idea is actually very interesting. So in fact, it would be very interesting if they can get their counterexample to work. Okay, so this is sort of a list of positive results. Let me try to give an example of a variety that does not satisfy this asymptotic enumerativity, and this will kind of indicate why I, at least for the moment, am requiring this Fano condition. Okay, so so in this example, I'm going to take X to be the blowup of PR at yeah, let's just take X to be any blowup of PR at points. Okay, so you can take any number, but in fact, this will be good enough if you take 2 points, say. And so this will be a non-Fano blowup. So I'm going to assume there exists a smooth rational curve on X. That's negative. So its degree against the anti-canonical is negative. So you already get an example of this phenomenon if you blow up, say, P4 at 2 points, because the proper transform of the line between those 2 points is negative. And okay, you can also get this example to work. You can actually get away with a curve of degree 0 if you're working with if you're blowing up P2. So for instance, you can blow up 3 collinear points at P2. Okay. All right. So then the claim is that this X fails to have SAE. So even asymptotically, these Gromov-Witten variants are not enumerative. And the reason is very simple. The reason is simply that because I have this negative curve, I can just take any, so I can build a stable map where one of my components is a sort of bad negative curve. And what does that buy for me? Well, if I take some multiple cover of that negative curve, I can kind of juice up the degree of this other component, right? So the more negative I make the negative curve, the more positive I can make the other component, which has all these mark points on it, and therefore the more degrees of freedom it has, right? And the point is I can give it enough degrees of freedom that there will exist a curve of kind of very large degree passing through these endpoints. And then I can just stick on a negative curve onto that and make a stable map that will always contribute to this virtual invariant. Okay. But the point is that when you're not Fano, of course you can't do this, right? Because you have no negative curves on which this will work. But sort of somehow the objective of this example is to show that this property is non-trivial, right? So I mean, some varieties have it and some varieties don't. Okay. So in particular, this is telling you that somehow for these blow-up examples 3 through 6, so I claimed that if you take the blow-up of P, let's say P4 at 1 point, then the Gromov-Witten variants are asymptotically enumerative. But as soon as I blow up a second point, then this will fail. Right. Okay. And notice I required my R to be at least 4 in that example. So when you blow up 4 points at P3, then I'm still okay. Okay. All right. So all right. Let's see. I have maybe about 10 minutes left. Okay. So I've stated a property of smooth projective varieties for which I want Gromov-Witten variants to be invariant, to be enumerative, and I've given you an example of some classes of varieties that do not satisfy the property. So in the remaining 10 minutes, I want to give some indication for, in the examples that we know this conjecture, how you might actually prove this, or how you might actually check this property in your example, right? So of course, I don't have no unified proof that works for all Fano varieties, but somehow the ideas are similar in all of these examples. Okay. All right, so I'm not going to go through this lemma in much detail. Let me just state the lemma and not mention the proof. Yeah. So the first thing you prove, this is actually a fairly standard statement if you talk to people who work on hypersurfaces and so on. So the first observation is that when n is not too large, so when the number of mark points is not too large, which is equivalent to saying that the degree is not too large, degree for beta, then this first property is going to hold. So if you assume your map is kind of virtually finite and n is not too small, then at least you can get off the ground. Then the geometric Tapilev degree will be defined because this map actually will be generically Étal. Okay. And in fact, for this, I don't need x to be final. Okay. So in particular, let me just say in particular. Whoops, sorry. So Tev, x, g, and beta actually makes sense because I have a finite set of points to count. And somehow the idea here is that, well, this is some kind of standard idea. Maybe I don't really recommend reading through this proof. The idea is that if you have kind of enough, so these points on x are general, and the idea is that the points on x also move around, and this gives you some kind of sufficient positivity on your curve class to show that there's no h1 when you pull back the tangent bundle, and this gives you some kind of local computation that allows you to show that basically deformations on the fiber are unobstructed. So that's sort of the idea. Okay, so let me not go through this. Okay, but I will point out that this bound is not sharp. So so here I've said that if n is kind of not too big, or sorry, not too small. So if it's bigger than like 2g, then my space of curves that passing through n general points has the expected dimension. But in fact, for projective space, you actually need no assumption on n. You just need n to be at least 0, because Brunel theory tells you that if you're over a general curve, right, with no mention of mark points, then general curves have kind of the correct number of maps to projective space, right? And in fact, I don't use the generality of the curve in the proof of this lemma. So somehow these are two orthogonal issues. And so if you go beyond projective space, it's an interesting question to think about. Like if you have a general curve mapping to just some random Fano variety. So like when can you prove that these curves move in the expected with the expected number of moduli? And it's as far as I understand, for hypersurfaces, this is already a very interesting question. Okay, so this is already giving rise to some kind of Brunel question, but outside the realm of projective spaces. Okay, and yeah, so in particular, like this in this lemma, somehow the only thing I'm using is that the points on x are general, but I do not use that the domain is general, that this curve is general, and somehow it seems to me that there's more mileage that one should be able to get out of this. Okay. Okay, so I've hopefully convinced you, or at least I've claimed that this kind of, I can get off the ground and I can define a geometric Tapilev degree, but then I still need to do what's really a harder task to check that there are no boundary contributions to the virtual degree so that it's actually equal to the geometric degree, right? So the question is, when can I prove that that this, whoops, I should probably have a bar here. So when can I prove that there are no components of the boundary of the moduli stable maps living over a general point? Right. And so and really, I mean, there are various reductions that one can go through, but really the main case one has to think about is when I have, again, so remember that my maps are kind of a priori out of a general smooth curve, but in fact, in real life, these curves will not be smooth. They'll be, they might contract after kind of deleting all these non-stable components. They might just contract onto smooth curves. So the main thing I have to worry about is some kind of almost smooth curve, but then with rational tails, each containing one marked point. So these rational tails are of course unstable, and when I contract these rational tails, these marked points kind of move back onto what I'm calling the spine of the curve, this vertical curve. And I'm asking whether, so if you ignore this red component for a second, So I'm asking whether I can find stable maps with this kind of topology that map to my X and pass through general points. Okay. And so the remark is that, well, what broke this before in these kind of bad examples, failing SAE, is that when X was not Fano, or when X had negative curves, I could just tack on negative curves and kind of increase the number of degrees of freedom on the rest of the curve. But if I assume X is Fano, I can't do this, right? Because all curves have positive degree. Right, so you might think, oh, maybe Nef would be enough, and that may very well be the case. But in any case, what I want to rule out is that, yeah, so I don't have any kind of bad maps that look like this. And in fact, I can also assume that, so in this picture, I've drawn kind of, I guess, n prime points on this kind of spine curve of genus G, and I guess n minus n prime rational tails, each of which have one marked point on it. But in fact, I can assume that n prime is pretty small, because if n prime is large, I can go back to the argument from before and basically argue that there's kind of very little that at least the spine curve moves in the, or basically actually every curve moves in a family of the expected dimension. And so because I'm in the boundary, that boundary component stratum will actually have the expected dimension. So the point is that really when n prime is small, that's the hardest case, because then I have no control over whether these, at least this vertical curve moves in a family of the correct dimension. It could just be kind of anything, and there might be many more spine curves than I might expect. And so the point is that, well, the game now is the kind of difference between the expected and actual dimension of the space of curves with this topology is basically controlled by H1 of the tangent bundle on this spine. Right. So on the tails, basically nothing really bad can happen because I have one moving point on it. And so those move in families of the expected dimension. But the point is, if I have, well, the kind of the failure of my spine curve to move in a family of the expected dimension is controlled by the H1. And if that gets beaten by the number of, basically by the number of tails, which I can assume is basically n, then I'm done, because the number of tails kind of cuts the expected dimension of this boundary stratum by 1. So every time so somehow the more tails I have, the kind of deeper of a boundary stratum I'm in, and the less likely it is to fail to have the expected dimension, right? So if the amount by which it fails to have the expected dimension is less than the number of tails, then I've solved the problem. And well, and you can really check this inequality in some examples. So for homogeneous spaces, this is easy because the tangent bundle of a homogeneous space is globally generated. So its H1 is bounded by a constant. And in particular, it will eventually be less than the number of tails, right? Okay, so this basically proves the theorem in the case of homogeneous spaces across Riemannians and so on. And for hypersurfaces, one can think about trying to bound this H1. And this is kind of a fun exercise to write down kind of the dumbest possible bound. So one can kind of write down the Euler sequence for PR and then restrict it to X and try to bound H1 of the tangent bundle for a curve mapping to your hypersurface. And this gives a certain bound. It's well, it's dE plus 1 plus some constant. And one can check this is less than n. So here the point is that I have a D over here, which is growing, and I have an n over here, which is growing, and I want to make sure that dE is growing slower than n is. And that will only happen when E is relatively small. And so this is where this kind of square root of R bound comes in from before. So when E is pretty small, this kind of very naive bound on H1 is enough to to kind of beat the number of nodes. But in fact, in general, I don't know how to do better than this bound, which is a little bit embarrassing. But somehow, somehow I have not been able to take advantage of any geometry of this hypersurface to kind of improve this bound, which is why this is still in conjecture. Okay. So the game here really, the game here really is, at least the roadblock is, if I want to prove this enumerativity property for some Fano X, say, this really boils down to bounding some kind of excess dimensions of curves. But in fact, there are excess dimensions of curves that, on the one hand, are general, and that on the second hand, at least sort of move a little bit, right? They have some mark points that may be moving around, and others that may be kind of moving around partially. So you might have some sort of very bad curves on X, but maybe you can also kind of bound how they the badness with how they interact with these rational tails. But there's sort of a lot of work to be done here. Again, so I have many examples in which I can kind of write down some bound that proves a positive result. But in the general case, I think there's a lot of work to be done. Okay, so I think I'll stop there. And thanks very much.